Morning, everyone. I'll be right back. Morning, everyone. How are we doing? Questions? Here's the problem with extending the winter break. As you know, there's nothing for free, right? So if we extend the winter break, that means that at the end, when April rolls around, we won't have finished the semester. It'll run into May. And, if a vaccine comes, everybody's going to want to be out of school, but we'll still have school. So I don't know that it's a good thing to extend the winter break and therefore extend the whole semester. I don't know. Is the sound working? Can everybody hear me? Thank you. Yeah. So I look, if the school decides to extend, who am I to disagree? But I don't know that it's necessarily a good thing. People will feel that it's a good thing right now, but at the end, I don't know. Plus, I don't know about you, but as far as I'm concerned, there's absolutely nothing to do during the Christmas break. I'm not vacationing anywhere. I'm not going anywhere. I'm not doing anything. Everything's closed. I'll just be home for nothing. Exactly. Yeah. So, 10 days, 12 days, that seems like quite enough time to get some sleep if you're not doing anything else. All right, anyways. So that's why I'm not sure. Well, yeah, absolutely. Video games to catch up on. Sounds like an excellent break, But, after 12 days of sleeping and playing video games, you're ready to come back to school. All right, let's get back to work. Questions? Anybody? Questions? I think we're gonna finish the material today. Material for the course. Yeah, I understand international students want to go home. I don't know that I'd be going home if I was an international student. I don't know that I'd want to be. I'm not telling you not to do that, but I'm like I said, I'm not traveling anywhere. I'm not doing anything. Yeah, exactly. I wouldn't want to re-quarantine, and I don't know. I'm going to leave that up to you individually. We're going to do antiderivatives today. Exactly that. But before we do so, let's do one more example of the optimization business. Let me change the height to capital H and radius capital R. Find the largest possible volume of such a cylinder. Michael, that's an excellent question. Well, this is not our last class, right? This is going to be the last of the new material. Next week, we're going to have class all week. We will, first we'll answer questions if students have questions, things you want to go over. And if we run out of questions, I will find an old final exam. I'll post it on my courses, and that's what we're going to do. Well, like I said, so next week, all we'll do is revision and an old final if we have no questions. I haven't spoken to Sean yet, but I'm sure he'll be willing to do a review session as well. So here it is. This is a very nice final exam type of question, right? They're giving you a hint here, base radius, in the sense that you probably want to make your cone upside down. Right, so here we have a radius of R, and the height of your cone is big H. I will post the old final for sure, absolutely. I'll do that over the weekend. And I haven't decided anything about the final. Well, I think you have an optimization problem here with the extra constants, right? This big R and this big H can be viewed as constants, right? I mean, they are constant, they are fixed, big H and big R, but we don't know what they are. And what do we want to do? We want to inscribe the cylinder. So you see the idea, right? You want the cylinder inside here. So you can have this one, you can have the slimmer one. Right? So you have a bunch of cylinders that you can fit inside the cone. Which one has largest volume? What do we want to do? So, let's say that you have this cylinder. What is the volume of the cylinder? Well, volume of a cylinder, the base is a circle, so 2 pi r. Well, the base is a circle, so the area of that circle is pi r squared. Let's call it little r, where little r is the radius of the cylinder, and little h is the height of the cylinder. So area of the base, and then you're stacking these in a height of h. So pi r squared h is the volume of the cylinder, and this is what you want to maximize. But of course, you recognize you've got two variables here, r and h. So is there a relationship between little r and little h, given that this is inscribed in the cone? Well, I mean, I'm sure you're seeing a cone, yes, but also a triangle, right? And if you look at this angle right here, right, let's call this angle theta, then tangent of theta is opposite over adjacent, right? So big R over big H. But if you're looking at the small triangle right here, the side opposite is little r. And the side adjacent, this side here, well, this height is little h, so that side right there has to be big H minus little h, because when you add this with that, you get the big H. So tangent of this angle, when you're looking at the small triangle, is little r over big H minus little h. And now these two together give you a relationship for either little r or little h. Let's say little r is big R over big H minus little h. So your volume becomes pi, here's your R, exactly, you treat big R and big H as constants, right? Because they are constants, they are given, right? You have a cone of some height, big H, and radius, big R. Even though you don't know what they are constant. So there it is. Let's maybe even clean that up a bit. Pi big R squared over big H squared. H minus H squared times H. And you know what to do. You want to maximize this. First of all, do we want to give a domain for H? How small can H be? Right? I mean, H can be very, very small, but it's always going to be bigger than or equal to 0. And how big can H be? Well, I mean, it's certainly not going to be bigger than the height of the cone. So it's somewhere between 0 and big H. Absolutely. Thank you, Michael. So let's differentiate. We only have one variable now, only little h. So we're going to differentiate with respect to little h, dv dh. This is just a constant. So here you've got a product, so product rule applies. You could have expanded that, but let's not even bother. Let's differentiate the first one, 2 h minus h times the derivative of the inside, leaving the other one fixed, plus leave the first one fixed, differentiate the second one. Derivative of h is 1. If h could equal 0, wouldn't cylinder not exist? Well, I mean, you'd have a, right? So, I mean, you're thinking to yourself, shouldn't this be an open interval? An open for h as well? That would be fine too. Why is the derivative of the inside -1? This is the inside. This is a constant. Derivative is 0 minus the derivative of h, which is 1. Right, the point is, if h is 0, or if h is big H, right, the volume is going to be 0. So nothing important is going to happen here. Because, you know, I mean, we've drawn cylinders just by looking, which have a volume that is not 0. So we're not expecting a volume of 0 to play an important role here. Effie is asking why we differentiated according to h. Well, we only have one variable. We only have one variable, namely h. Constants don't stay the same. The derivative of a constant is 0. Thank you, Andre. Right, so we have rewritten everything in terms of h. We have the one variable h. We differentiate with respect to h. You had options here. You could have rewritten in terms of r. So written this h in terms of r, and then you would have differentiated with respect to r. You would have gotten a different interval for r, but of course the answer would have been equivalent. Why don't we differentiate r squared over h squared? This is a constant, in the same way that this big H was constant as well. Let's factor out an H minus H, leaving us with minus 2H plus H minus H. Or H minus H, H minus 3H. It's easy to read off the critical points. What are the critical points? right? You've got a problem. First of all, this derivative exists everywhere, right? So critical points are going to be where the derivative is 0. This is just a constant, so that's never 0. So we either need this to be 0 or that to be 0. And as everybody has pointed out, h is h over 3 or big H. Is that clear, everyone? Questions? But if the cone is H, exactly, right, the cylinder would be infinitely thin, right? You wouldn't have any. In fact, if the height is H, the radius has to be 0, right? This is the radius. If little h is big H, this whole thing is 0. The volume is going to be 0. And this is going to be nothing good. Let's draw a first derivative chart to understand what's happening at h over 3. H over 3, which is, of course, between 0 and h, right? So if you take a value close to 0, but just bigger than 0, this is going to be close to 0, so that's going to be positive. This is going to be close to 0, so that's going to be positive. And this is always positive, so the whole thing is positive. And if you take a value close to h, but just less than h, number close to h, but just less than h, this is going to be positive. If you take something close to h, this is going to be close to 3h. And h minus 3h is going to be negative 2h. So this thing is going to be negative. So negative, positive, positive, the whole thing is negative, which means your function is decreasing. So you see that you have an absolute maximum occurring at h over 3. And what was the question asking? Find the largest possible volume. So we can plug this little h into there. The volume at h over 3. There it is. So this is pi r squared. This is 2h over 3 squared is 4h squared over 9. The h squares cancel, and then you've still got an h over 3. So 4 pi r squared h over 27 is apparently the answer. Anybody else have that? How are we doing here? So this is the maximum volume. Was it complicated? I didn't think that was complicated at all. I thought that was very straightforward. This would make an excellent final exam question. I think you guys are saying that because you want an easy final. Well, I mean, you don't have to go that fast, right? I mean, you can do this on paper. There's no issue there. People were asking where did the 4 come from? I mean, just do it. H minus h over 3, that is 2h over 3. And then you square that. That's 4h squared over 9. The h squares cancel. Would you have to state any laws? Just what I wrote down. I think I did not skip any steps here. I showed all the work. Can we re-explain why it's positive between 0 and h over 3? We have to go back to the v prime, which I have conveniently erased. Let's think about what it was. R squared over h squared. H minus h. H minus 3h. Was that the derivative? Yeah, exactly. As Seelan points out, the only challenging part was noticing the similar triangles. Thank you, Willem. But in your original volume, you had both a little r and a little h. So you knew that you were looking for a relationship between the two. Because you don't want to be differentiating functions of two variables. That's going to be later on in calculus 3. Here, you wanted a relationship. You want a function of only one variable. You know how to maximize a function of one variable. And that's what we wanted to do here. So that was the derivative. If you take a number close to 0, well, look, I mean, again, you can take any number in here. So if you want a specific number, take the midway point. What's midway between 0 and h over 3? Give me a number that is in here. H over 6. H over 6 is between 0 and h over 3, right? It's the midway point. So plug in h over 6. If you plug in h over 6 for little h, here you get 5h over 6. And if you plug in h over 6, here you get big H over 2. Both of these terms are positive. My argument was, take a number very close to 0. As close as you want it to be. Matt is suggesting some number, but we're going to be in trouble if h is actually smaller than that. Right? So you can't really plug in a number, but it's more of an argument. If you take a number very, very close to 0, this is going to be very close to 0. So the thing in brackets is going to be close to h. Exactly that. And if h is very close to 0, this is going to be very close to 0. So in the square brackets, the term is going to be very close to h. Positive, positive. There it is. How are we doing? Let's go back to the antiderivative. We already introduced it, right? For those of you who were taking physics. Instead of, right, I mean, if you start with a function like x, you know the derivative, right? You know the derivative of x. we want to do the opposite. If you start with x, we are asking what function has derivative equal to x. In other words, what function has its derivative x? And we call that the antiderivative. So notation, try refreshing. Is it working better now? Is anybody still here? How are we doing? Better now? Very good. Good. Right, so let's introduce some notation, which we already saw before. This is notation for the antiderivative. We're looking for a function whose derivative is x. Now, since you're all experts in differentiation, you can work backwards in your head. What function has derivative x? You know what the answer is. 1/2 x squared. Right? Because when you differentiate this, you bring the 2 down, which cancels with the 1/2, and you get x. But you know that the derivative of a constant is 0. Right? So if you add 1, this is still the derivative, or 4, or 47, and so on and so on. In fact, if you add any arbitrary constant, this is still the antiderivative. And from a corollary of the mean value theorem, we saw that if two functions have the same derivative, then they differ at most by a constant. So this incorporates, this is the whole family of antiderivatives. Every antiderivative of x has this form. There are no other functions other than this, which are the derivative, whose derivative is x. How are antiderivatives related to integrals? They're essentially the same thing. This antiderivative is sometimes referred to as an indefinite integral. So it's the same thing. What function has as its derivative x to the 1/2 or square root of x? Work backwards. You know how the derivative works. You know how the derivative works, right? You bring the power down and you subtract 1 from the power. So as Michael suggests, 2/3 x to the 3/2 plus your arbitrary constant, right? And you know, that's the beauty of the integral, because whatever answer you give, you can always check by differentiating. If you differentiate this, you have to get that back. What is the derivative? You bring the 3/2 down, it cancels with this, and you subtract 1 from the power, getting x to the 1/2. Very nice. Now, can we generalize? Can we get a nice formula? You know, the derivative of x to the n is exactly that. Exactly that, but we're going to get a general formula in a moment. You know the derivative of x to the n, right? The derivative of x to the n and x to the n minus 1, right? You bring the power down and you subtract 1 from the power. If you want to do the opposite now, if you're looking for a function whose derivative is x to the n, or an antiderivative of x to the n, you had better have started out with a power that was 1 more than the original, right? So you need 1 more because you're going to subtract 1 from the power, but you're also bringing this down, and you want to compensate for that, right? So you need a 1 over n plus 1 up front, right? When you differentiate this to verify, you bring the n plus 1 down, so it's going to cancel, and then you subtract 1 from the power, getting exactly x to the n. So we have this nice formula now. The antiderivative of x to the n is 1 over n plus 1, x to the n plus 1. Observe, in this case, if we apply that, 1 over 1/2 plus 1, x to the 1/2 plus 1. Or 1 over 3 over 2, x to the 3 over 2. And 1 over 3 over 2 is 2 over 3. Works nicely. You also know that the derivative is linear. Right? The derivative of a product is the product of the derivatives. No, sorry. Let's write back. That was terrible. The derivative of a sum is the sum of the derivatives. And the derivative of a constant times a function is the constant times the derivative of the function, right? So the antiderivative has to work in exactly the same way, because when you're checking, by checking, this is satisfied. So the antiderivative has to work in the same way. In other words, the antiderivative of a sum is the sum of the antiderivatives. And the antiderivative of a constant times a function, you can just take the constant out. Right? Those of you taking linear algebra, this is known as the linearity property of the integral. In the same way that the derivative is linear, the antiderivative is linear as well. Let's take a few examples. Before we take an example, let me bring your attention. How do you indicate what's outside the antiderivative? What do you mean there? I don't know what you mean by outside of the antiderivative. Oh, did you mean just this c here? It's outside, right? I mean, because it's c times the integral. Yeah. Well, I mean, here it was inside. I'm saying you can take it out. That's what I'm saying. Since it's constant, you can take it out. In the same way with the derivative, right? When you differentiate c times a function, you can just take the derivative of the function and yeah, on the left, all is inside. So whatever is between the integral and the dx is inside. Yeah, the dx closes it as Zoe suggests. Yeah. So whatever is sandwiched between your integral sign and the dx, this is known as the integrand. Whatever is inside the integral is known as the integrand. Jacob hears that an integral is an area under the curve. Are we going to go through how that works, or is it for next semester? It is for next semester. But you're absolutely right. It represents the area underneath the function above the x-axis, if your function is positive. What I wanted to bring your attention to here is the fact that we have an issue with this formula when n is -1, right? Because if n is -1, you have a 0 in the denominator here. So that's not going to make any sense. Seelan, as far as we're concerned, antiderivative and integral is the same. There's no need to make a distinction. As far as we're concerned, it's the same thing. There is a slight difference in the sense that, as Jacob was pointing out, sometimes the integral is going to represent the area underneath the graph, whereas here it just represents the antiderivative. So look, I mean, as far as we're concerned, antiderivative and integral, same thing. We'll discuss the subtlety in 141, but for now it's the same thing. So it's just an antiderivative. Here we have an issue, right? If n is -1. So let's address that. Willem, what are you bringing up? The difference between antiderivative and integral? It's fine, no worries. It's the same thing. It's the same thing. So let's not worry about it. My question to you is, what function has 1 over x as the derivative? Or what is the antiderivative of 1 over x? Ln of absolute value of x plus c. Absolutely. Let's take a few examples from the book. Why ln? Well, you tell me. What's the derivative of ln? Right, derivative of ln x. Derivative of ln x is 1 over x. There it is. We were looking for a function whose derivative was 1 over x. The answer is ln x. Ln of absolute value of x, right? Because if you remember, back in the day, we showed that the derivative of ln of absolute value of x was actually 1 over x. So we want the most general antiderivative, ln of absolute value of x. Look at this. We're looking for a function whose derivative is x squared minus 3x plus 2. Right? As Michael suggests, By this argument, you can find an antiderivative for each piece. Antiderivative for x squared, antiderivative for minus 3x, antiderivative for 2, and just add them together. What function has, or what is the antiderivative of x squared? Well, you can use that formula. Michael has given it to us. 1/3 x cubed. What function has derivative minus 3x? Or you can leave the minus 3 outside and ask the question, what is the antiderivative of x? The antiderivative of x is 1/2 x squared. What is the antiderivative of 2? What function has as its derivative 2? Answer is 2x. Throw in your arbitrary constant and you're done. 1/3 x cubed minus 3 over 2x squared plus 2x plus c. Notice that you can verify your answer here. Willem doesn't like the dx at the end and would prefer to put brackets. That's fine. Brackets are fine. Go ahead and do that. Don't put the dx in brackets though. Rather put the function in brackets if you want. But again, don't let that scare you. The integral dx is just notation. We're not going to do integration by parts though. So this is just notation. Don't let anything fool you here. And it's the function that's inside that's of importance. Everything else is just notation. Right, I was going to point out that we can verify our answer here by taking the derivative. Let's take a moment to check. We can check by taking the derivative of the answer. If we're right, the derivative should give us what we started out with. Let's see what happens. The derivative of x cubed is 3x squared. Derivative of x squared is 2x, and the derivative of 2x is 2. The 3's cancel out, the 2's cancel out, leaving us with x squared minus 3x plus 2, exactly what you started out with. So you know you're right. That's the beauty of Cal 2. All right. Let's repeat. What is the antiderivative of this thing? We can do each piece separately. Leave the 6 out. Antiderivative of x to the 5. 1 over 6. X to the 6. Leave the minus 8 out. Antiderivative of x to the 4. 1 over 5. X to the 5. Leave the minus 9 out. Antiderivative of x squared. 1/3 x cubed. Throw in your arbitrary constant. Maybe clean that up a bit. The 6 is canceled. So you get x to the 6 minus 8 over 5 x to the 5 minus 3 x cubed plus C, exactly as Michael suggested. How are we doing with the antiderivative here? You see the danger though, right? Two things are dangerous. First of all, it's dangerous that if you're not comfortable with the derivative, some people are going to confuse the derivative with the antiderivative, and that will be costly on an exam. So you have to be very comfortable with the derivative to understand that you're now doing the opposite and not getting the two confused. I mean, there really shouldn't be any confusion, right? Because one of them is this, and the other one is this. They don't look anything alike. So, but yet some people do confuse them. And if you confuse them, I'm going to suggest that it's because you're not comfortable with these concepts. You're not comfortable enough. A second issue is that you don't want real-life application of the antiderivative. As a few people have suggested, it will, and as you'll see in 141, it corresponds to the area underneath the graph. So you can use the antiderivative to calculate areas. We're not going to see that in this course, but that's the starting point in 141. Now, Michael has in fact given us the right answer, but one danger of the integral or the antiderivative. Varun, nice to see you again. One danger of the antiderivative is that you start making up your own rules. And we want to stay away from that. So let's not make up any rules. What do we know so far? We know how to find the antiderivative of powers of x. And we don't have that immediately here. But if we expand, then you have simple powers of x, which you can integrate term by term. Antiderivative of x squared, you know what it is, 1/3 x cubed. Antiderivative of x, 1/2 x squared. Antiderivative of 25, 25x. Throw in your arbitrary constant, you're done. Let's clean that up. Why is there no antiderivative wet work? It's a good question. I don't know, but we have. I've uploaded all the web works that there were, so that's it. I mean, there will be no new web work. Why did we not do the antiderivative for the chain rule? It's an excellent question. Yeah. It's an excellent question, and this, in fact, will be the first technique of finding antiderivatives, the first technique of integration that we're going to see in 141. The date of the final, it's been posted on, I've given a link to the exam schedule. How much does web work count for our final grade? I think it's 30%, is that right? 30% assignments, 30% midterm, 40% final. There it is. And we can check our answer, right, by differentiating. Can we do that quickly in our head? The derivative of x cubed is 3x squared. So the 3's cancel, you get an x squared. Derivative of 5x squared is 10x. And the derivative of 25x is just 25. Well, the U substitution we're not going to do in this course, right? It's going to be, like I said, the first technique of integration we're going to see in 141. So in the final, you would have to expand before finding the antiderivative, correct? Partial fractions, well, they will come soon enough, you'll see. Consider this, right? I mean, some people are going to be tempted to find the antiderivative of this, to find the antiderivative of that, and multiply them together. Of course, you know that doesn't work, because when you try to take the derivative of a product is not the product of the derivatives. Mara, you're correct. If you get 100% on the web work, that's already 30% of your final grade. It becomes very difficult to fail the course at that point. Questions? So, right, I mean, you're not going to find the antiderivative of one part, the antiderivative of another, and multiply them together. You know, even when, because in a regular semester, the web work is only worth 10%. Or 10 or 15%. And there's a usually high correlation between those that fail the course and those that did not do the web work. So most people who do the web work and get 100%, I mean, I don't mean just plug in any answers and say they've done it, but people who really do it and get 100%, it becomes very difficult to fail the course if you have 100% on the web work, even if it's only worth 15%. So, you know, normally people who don't do well are people that didn't take the course seriously. So what are we going to do here? Expand. Expand everything first. Rewrite everything in terms of powers of x, and then integrate term by term. Your only formula is for powers of x. So this is 2 root x, or 2x to the 1/2. This times this, x to the 3/2. this times this, x to the 5 over 2. Understand, absolutely right, expand and distribute. Understand that I have not integrated yet. I have not found an antiderivative yet. I just rewrote the integrand in a way that I can deal with. Now, let's find the antiderivative. Leave the 2 outside. Antiderivative of x to the 1/2. 1 over 1/2 plus 1. X to the 1/2 plus 1. Antiderivative of x to the 3 over 2. 1 over 3 over 2 plus 1. X to the 3 over 2 plus 1. Leaves a 6. Antiderivative of x to the 5 over 2. 1 over 5 over 2 plus 1. X to the 5 over 2 plus 1. Throw in your arbitrary constant, and there you go. How did the 6 become a 5 over 2? What? I'm not sure what you mean here. The 6 is still there. Still the 6. It used to be x squared, but x squared times x to the 1/2. Maybe that's what you mean. X squared times x to the 1/2 is x to the 5 over 2. Let's finish that up. This is 1 over 3/2, so it's really 2/3. So that is 4 over 3, x to the 3 over 2. This is 5 over 2, so if you flip it, it's 2 over 5. X to the 5 over 2. And this is 7 over 2. So if you flip it, it's 2 over 7 times the 6. 12 over 7. X to the 7 over 2. Throw in your arbitrary constant. There you go. I'll leave you to verify. But if you differentiate this, you should get this back. How are we doing here? Questions? Seems like a good place to end. Well, actually, I actually had more prepared, more antiderivatives. So we'll finish that up on Monday. And I will find an old final somewhere. I'll find an old file somewhere. I'll post it on my courses so you can have a look at that. On Monday, we'll finish this up. We'll answer questions you may have. And if there are no questions, we'll start looking at the old final. Well, this is very easy if you're comfortable with the derivative. If you're very comfortable with the derivative, it's easy to work backwards in these simple examples, right? In these simple examples. Because, of course, antiderivatives are much more difficult in general than the derivative. And I'll tell you why. In the derivative, if your function is a quotient, you apply the quotient rule. Case closed. If your function is a product, you apply the product rule. And that's it. So you have these rules for differentiation. There's no guesswork. In antiderivatives, you have techniques. There are no rules. So you have this idea, that idea, you can try that, you can try this. There's no set rule to tell you what to do. I mean, of course, unless it's an expression made up only of powers of x, then there's really nothing happening here. But example, what if you had But if you had this, I'm giving you a very easy one here. I mean, we're distributing, right? So it's x to the 1/2 times x squared. I'm waiting to see what the equation was. Very well. Zero is also a critical point, but I believe, and you can correct me if I'm wrong, but I believe the domain was this. So that 0 was not in the domain. So that 0 is not a critical point. Because by definition, critical points have to be in the domain. There it is. Well, I think the question he was referring to, we had round brackets, meaning not including 0. If you did have square brackets, that would have included 0, and then 0 would have been a critical point. The lecture is over. Thank you all for coming, folks. You guys have a good weekend, and I will see you on Monday, where we'll finish this up and take it from there. Have a look, be on the lookout for an old final that I'll post, and I will see you on Monday. You guys have a good one.